Now that we've learned about capacitance, we actually can do an experiment we've never done before, which is to measure the charge on something. Up till now, we've always just basically given you charges. We could see that based on our definition of capacitance, charge on a capacitor will be equal to the value of capacitance times the potential difference between the sides of the capacitor. You can therefore think of capacitance as being like a conversion factor. If we know the potential difference in something, we can use capacitance to convert back and directly measure the charge. This picture is from a 1917 physics textbook called the Hawkins Electrical Guide. It's describing an 1840s experiment by Michael Faraday, which we can use today to measure the charge on an object. This is a metal ice bucket, and Faraday has connected the outer surface to an electroscope. It's insulated from the ground, and he's going to lower this ball K, which has a positive charge, into the bucket. What that's going to do is induce a charge separation in the bucket. Electrons are going to flock to the inner surface of the bucket to try to get as close to K as possible. That will leave a positive charge on the outer surface, which the electroscope can measure. Using more sensitive instruments today, we can use the size of the potential difference on the ice bucket from ground to go back and make an indirect measurement of the charge on the ball. So here's the modern day experiment as produced by PASCO. The ice bucket is actually this inner wire screen here. I've got the object in it, although we've got no charge on it at the moment. The outer wire screen is just a shield to prevent any electric fields from outside from causing a problem. It's set as the 0 for our potential difference readings, and the outer cage is wired not only to 0, but to the ground through a water pipe, basically. It's hooked up to the meter. So this is always going to be at a potential of 0, and the potential of the inner cage is going to be entirely due to the induced charge caused by putting the conductor in it. So the math you see here comes entirely out of the PASCO manual for our electrometer, which you can find on their website. And the theory of it is that to find the capacitance of the ice pail and the electrometer so that we have a conversion factor where we can convert the voltage it reads to a charge, we employ a second capacitor. The charge on that capacitor will be its capacitance, which we know, times whatever voltage I use to charge the capacitor up. We then connect it in parallel with the ice pail and electrometer, and that charge will then be shared throughout both capacitors and the meter. So the charge that we put on the capacitor originally will be equal to the charge in the whole circuit finally. We know that capacitors in parallel simply have their capacitances add together. So the original charge, the original capacitor's capacitance times its voltage, will be equal to the final charge, the combined capacitances, times whatever voltage the meter decides to tell me. So by doing that, we can do some algebra and we can solve down to figure out what the capacitance of the electrometer is. Once we have that, we then can use the equation Q equals CV. Whatever voltage it reads when we put the charged object in there, we can use that to estimate the charge on the object. Let's see what this looks like when you really try to do it. So I don't know if you can see the little orange dot that's between the two clips of these alligator clips. That is a small capacitor. It is rated at 33 picofarads, which is 33 times 10 to the minus 12 farads. It holds a very small amount of charge. What we're going to do is plug that into a power supply, which I've got set for 35 volts, and that is over here. And that'll put a known amount of charge on this capacitor. We'll then hook it up across the Faraday ice pail, measure the voltage on the electrometer, and we'll be able to figure out what the capacitance is for the that setup. So we're now going to take our capacitor and we're going to use it to figure out how much capacitance this Faraday ice pail here has. So I'm going to grab myself, I'm going to zero my meter. I'm going to grab my capacitor. Careful not to let the two leads touch each other. And we'll hook one of them up here and one of them up here. And I got 18 volts. So what we'll do is we'll plug that into this equation and we'll figure out what the capacitance of the electrometer is. So again, operating under the principle that the charge on that capacitor, once hooked up to the ice pail and the meter, will spread throughout the meter and it'll be the same charge. PASCO used that equation to solve for a way to find the capacitance of the meter and bucket. And here's our solution. We've got our known capacitors. We've got the 35 volts we charged it with. We got the 18 volts the meter read. And when you solve all that out, you get 3.11 times 10 to the negative 11th farads. So notably, that's a little bit bigger than our 33 picofarad capacitor. It's about 300 picofarads. So now that we have a value for capacitance of the ice pail and meter, we can use it as a conversion factor to solve for what the voltage on the meter reads. We can turn that into the charge on the object that's been put inside the ice pail. Now we're going to be able to check exactly what charges are on different objects. So the first thing I wanted to do was remind you about my Wimshurst machine. And this thing is capable of producing some fairly impressive sparks. And we'll just kind of demonstrate that again. I've got the two storage jars which store a lot of charge hooked up. And we'll see how much I have to crank this in order to break down the air. So we'll crank. If you notice me looking, I'm looking over at the electrometer to see if it's affected at all from this distance. It doesn't appear to be. So I was cranking for a good 20 seconds before we got our first lightning bolt. So these aren't that impressive lightning bolts. My students are always a little underwhelmed by it. But I think it would be interesting just to consider how much charge there is there. So what we'll do is we'll take off the charge storage devices. They're out of the equation. And I'll just give it one crank. And we'll see if we can figure out how much electric charge is generated by just that one crank. So separate the two pretty far apart. I've got my ping pong ball covered in conductive paint. I'll discharge that. Hold it by its thread. And I'm just going to give this one crank. So watch what happens when I bring the ping pong ball close. I don't know if you saw that, but it was attracted because it was neutral and its electrons had an induced charge. And now it's got whatever charge this one ball had. So we'll go over to our Faraday ice bucket and we'll check. First of all, I want to discharge myself. And this thing has a limit of 100 volts. And I actually can't put this inside yet. It's too much for this voltmeter to actually measure. So I'll just sit here and talk for a minute and we'll see if it discharges. And once I can get it in there, it can get a stable reading, we'll calculate just how many extra electrons there are on this thing. After that, I'll do a somewhat cruder demo in a separate video. I'll just rub some rabbit fur on my shirt, we'll charge up the ball that way, and we'll check how many electrons that transferred. So are we ready? Still can't go in there. So I'm going to stop the video at this point, but we'll figure out how much charge is on there after, I don't know, I'll keep timing. We'll tell you how many minutes from this it actually ends up being. So about 3 minutes after that, I was finally able to get the ball into the ice bucket, and that made the electrometer read 84 volts. Let's take a look at that. So here's the electrometer reading 84 volts. You can see the ball is about halfway. It's in the middle of the ice pail. And again, this is 3 minutes after the end of the previous video. It took that long for the atmosphere to slowly carry charge away, enough that I could safely put the ball in the ice bucket. In the video, you saw me having it like up here, and it was reading 100 volts, which is the maximum range of the meter. I would have broken the meter if I had continued to lower it in there. So let's try to figure out how much charge that is and how many missing electrons on the ball that represents. So we'll use our capacitance we calculated before as a conversion factor to turn that 84 volts into a charge on the ball. And when we do that, we can see that we get 2.61 times 10 to the minus 9th coulombs, which seems like a very small number. But you got to remember that a single electron only carries 1.6 times 10 to the negative 19th coulombs. The coulomb is a huge unit. So when we divide that charge by the charge on an electron, we get 1.63 times 10 to the 10th electrons, a huge number of electrons that are missing from that ball. And that was 3 minutes after we let the atmosphere bring electrons back to that ball. Let's charge the ball using something more typical, different cloths rubbing on each other. We'll see what kind of charge difference that creates and how many electrons that represents. And the calculation you should have just seen is that it's more than 16 billion electrons on that ball from one crank of the Wimshurst, and then waiting a good 4 to 5 minutes for the atmosphere to carry electrons away. Even small amounts of charging, though, can produce relatively large numbers of electrons transferring. So I just want to check and make sure I've got the ball totally discharged, and I do. And what I'm going to do now is I'm just going to take the rabbit fur we used from that first electrostatics experiment, move my ID out of the way. I'm just going to rub my chest a little bit. So that should put a charge on the rabbit fur. I'm going to put that all over the ball. And now we'll stick the ball in there. We'll see how many electrons just from that transfer there was. So this is reading minus 15 volts. So here's the calculation for 15 volts. The minus 15 means it's the opposite charge that we had from before. So we'd use our same capacitance to convert the 15 volts into a charge in coulombs. And it's obviously a smaller charge than what we had from before, but it still represents almost 3 billion electrons. So a ton of electrons get transferred, even in common things like scuffing your feet on the carpet or rubbing two fabrics together.